Hello and welcome everyone to today's Association for Manufacturing Excellence webinar titled Creating Assembly Lines in a High Mix Environment. I am Darlene King, Director of Administrative Services for AME, and I will be your moderator. Today's presenter is Greg McFalls. Greg McFalls is the President of McFalls Technical Solutions, Inc., and a lean practitioner and enthusiast. After working in environments with millions of variations, McFalls has developed a technique for dealing with the issues of planning, executing, managing, and improving production while facing very difficult challenges. Before we start, just a couple of housekeeping items. You will be in listen-only mode throughout the webinar. You will see that you are muted on your attendee panel on the right side of your screen. If you have questions during the webinar, please type them into your question area in the attendee panel and click on Submit. We'll review the questions at the end of today's presentation and answer as many as we can. When you log off today, please check your email inbox. In it will be an invitation and link to fill out a short webinar attendee survey. Please take a few minutes to complete the survey today, as your feedback is very important to us to improve future webinars. We will be sending a recorded link for a webinar replay to each of you next week. Now, I am pleased to introduce Greg McFalls, who will present Creating Assembly Lines in a High Mix Environment. Take it away, Greg.
Hey, thank you, Darlene. You know, it's funny, I've struggled with this high mix assembly for well over 10 years now. And so I feel the pain that companies must have when they have, you know, a lot of models, a lot of variants going down an assembly line, and how to run that nice and smooth. And so we'll talk about that in this webinar. And we'll start off with my humble beginnings and how I got started and how I faced the same challenges probably other people on this phone, on this call have faced as well. And so as our company struggled, we embraced lean manufacturing, and that really began the change of our company culture. And when we started lean manufacturing, the way we were trained on it was that variation was an enemy. You know, we wanted to set up our production areas where we had as little variation as possible in each production area. So if I had, let's say, 4 different models, A, B, C, and D, I would have an area for A, an area for B, an area for C and D. And so, and that worked out pretty well. We had a lot of milestones from that. And as we started to work through our, as our company grew and we got more complicated and more complex, we ran into a hurdle with our production system, and we had to go take another journey, another leap forward into mixed model production. And that's what we're going to learn today. The production model we're going to learn today is assembly only. For fabrication environments, we have a different system for that. So for this here, we're doing assembly only. The company that I worked in assembled slot machines. Toyota assembles cars. So we do this assembly assembly system to help the assembly line run nice and smooth all day, considering some might be hard and some might be easy. And we'll look at some benchmarks to see how that might have played out as we work through our journey and how everything worked out and the milestones we were able to achieve as we went from our old production system all the way into mixed model production. And then we'll talk about your questions. You know, as Darlene mentioned, if you have any questions, go ahead and submit them in the webinar, and we'll get to them at the end as time permits. But I'm sure, like most of you, you're probably struggling with mixed model production or high volume assembly, and so did I. In 2005, I went to go work for Valley Technologies in Las Vegas. They were a leading slot machine manufacturer, and their lead was being challenged by their competitors. They were having a harder and harder time getting a bigger piece of the pie, and they realized that their customers, their casinos, they wanted their floors to look different. They wanted more variety of their machines. They wanted more, bigger monitors. They wanted machines that were taller, some that were shorter, some that were sit-downs, these uprights, some that were slants. They wanted a bunch of different models, and they wanted their floors to look very creative as you walked into them. And Valley saw this as an opportunity. They went in on this premium slot machine business where they could provide these premium machines, these machines that had huge monitors, these machines that had these great options to them. And premium to us meant more and more options, more models, more option sets, more configuration sets for each customer. And so for each customer, we're going to sell fewer models to those customers. So instead of selling 50 of one model, we still want to sell 50, but we're going to sell 2 of these and 1 of those and 2 of these and 3 of those. And it changed the way we produced that product. And so we had more and more sales order variation as customers ordered. In 2006, the customers couldn't get enough. They loved it. They loved how their floors looked. They loved how the machines worked. They loved it. And they ordered plenty of machines with Valley. We just couldn't produce them. We struggled mightily on our manufacturing, in our manufacturing floor, because we just weren't set up to run orders that way. The way our floor was set up, it was, this is 200 by 150 square feet. And these production lines would produce the product down these lines here. Now, these are long lines. This is a big square footage here. In raw material, we had a raw material warehouse where we would order the material from the warehouse. It would be brought over in a truck into these racks into pallets, 15, 20 pallets at a time. And the operators would go to the pallets and get their parts and be able to assemble it as they go. And that worked okay when we were building a wide, you know, a lot of the same machine over and over again. But when you're building one of these and two of those and one of these and three of those, this system became challenged. We had 500 pieces in WIP. We had 240 people in assembly doing 100 units a day. We had problems with quality. We had problems with BOM accuracy. It was just an issue in how we produced that wide variety of products. And this is kind of how this looked. This is how the floor looked to us. Now, this isn't our floor. This is a video, or sorry, a photo that I found on Google, but it really represents how our floor looked as well. In fact, most slot machine manufacturers look this way. These huge monster floors with these big long lines where they had lots and lots and lots of machines all over the place. The only thing missing here would be the racks of parts, is really the only thing missing here. Here, the parts are all over the floor. But this is kind of how this looked. Huge square footage, lots of machines. And so when I got hired in 2005, I was a manufacturing engineer. How do I help us manufacture these products better? And that role was good for me. I liked that role. I liked being an engineer, and I liked trying to solve problems. I was just focused on very narrow problems was my issue, right? I'd be like, how do I build the reels better, or how do I solve this quality problem? And I didn't really have a real great understanding of all the issues that manufacturing environment was creating until I had to go manage a customer. I became a project manager for one of the major customers, and it quickly became apparent that our production process had many problems, right? We weren't predictable, we weren't flexible, we weren't productive. You couldn't tell me when games were going off, you couldn't tell me when games were going on, what the status of them were. It just wasn't a flexible system. And I started looking at this and I was like, there's no way we're making money. This is how we produce product for customers. How could we be making money on this? So I started looking at the financials, and I'm like, we lost 50 million in 2004. We lost 50 million in 2005. We're clearly losing money. Like, this is not a productive way to do this. And at that same time, our vice president decided to go on to another venture. Basically, I think he just had enough of Valley, quite frankly, and he went to go work for somebody else. And so we're looking for a new VP. And the new VP that was hired was Doug Mack, who became my boss, right? I didn't have any responsibility for hiring Doug. I'm just an engineer, but he was the person they hired in to take over production, and he changed that business forever. He's the boss that you hope you have, right? He brought in lean manufacturing. He taught us all about waste and flow and value and how to really appreciate the value of production. And he started off with a Kaizen event. 2 weeks into his job, he wants to run a Kaizen because he just knows there's a better way to do this. And so we started off with a C9 production line. And so he taught us all about wasteful activity. Here's our C9 line. And he taught us that having all these lines on this whole big, all these games on this whole big line is wasteful activity. It's wasteful to put all that stuff up and just let it sit on the line. It's wasteful to have 3 different warehouses, one for raw material and bring it over into pallets and let it sit in racks that we'd have to dig off of. And then those games will then go to a finished goods warehouse. That was wasteful to do that. He wanted us to focus on the value, right? The value is us building the machine. How do I get to the point where the operator can build the machine like a surgeon? And so we redesigned the production line, and that was our focus. And so this line became a lot smaller. We did this line, and the games came up. We had position 1, 2, and 3, where the parts were presented right near the operator. They didn't have to move around at all, and our water spider would fill this like a Kanban. And this worked incredibly well. And we were able to do 30 units a day instead of 20 units a day. We had 8 people instead of 22. Our square footage went way down because the line went a lot smaller. And the wasteful activity went, just in 1 week, we had a huge improvement on how we produced this product. And so as managers are looking at this, they're like, why aren't we doing this everywhere? This is phenomenal. Like, why don't we just do this all over the place? So we did. We redesigned the production floor to use cellular production everywhere. And we're able to get our same 100 units per day out, but now we're doing with 85 people. So we're doing with far less people and far less square footage. In fact, we were able to get rid of our finished goods warehouse, and we were stocking finished goods here and shipping right out of this warehouse. And this became our raw material, on the left side became our raw material storage, so that we could then kit the material and bring it to the lines, so that the lines got kitted material on the line. And the improvement this had on the business was unbelievable, right? We became, not only were we getting rid of a warehouse, we're having less people, we're producing the same amount of units, but we got more flexible. We had just-in-time inventory with some of our suppliers, so we weren't bringing huge cabinets in. We're bringing in the cabinets every couple of hours, and only for the cabinets we need for production. Everything got better, and we were able to do all that in 16 months. In a very short period of time, we drastically improved that business. And we didn't just work on the production lines, we worked on the systems as well. We developed a work instruction system because we had all these different options and all these different models. We needed a way to present the instructions to the operator in a nice, smooth way. So we worked on that. It had a pretty advanced algorithm for that. And we had an advanced scheduling system we worked on as well, so that we could schedule these lines and have them run nice and smooth. We developed workstations with cardboard and aluminum. We didn't buy the workstations, we built them ourselves. And same thing with our systems. We built those ourselves. We built our material delivery system. Our TPRS system is what we called it, that controlled our raw material and our software and stuff. So we got a lot of questions of like, have you ever thought about custom designing your hardware? Well, yeah, we not only custom design the hardware, we do the software as with it. And that allows us to drive improvements at a rapid pace. Paul Akers at FastCap has this idea of 2-second lean, and we really bought into that. If you have an idea for improvement, we want to hear it, and we want to make that idea come to fruition as soon as we can in production. And we were getting hundreds of ideas every year on how to make this thing better and better and better. And so that sounds great, sounds awesome. Like, oh, we must have been amazing, right? But it wasn't without its problems. It was better, but better is not amazing. It's just better, right? And so as we started to make these games with these cells and stuff, and we were able to take out some of the warehousing and save some costs, that freed up a lot more money for R&D. So R&D wanted to make more games. Let's pump R&D in and let's engineer more premium games, more models, more option sets, more configuration options. And so the cells that we had were handling a greater and greater variety. And this became a serious issue. So if our C9 cell is running C9s, maybe sometimes they're running a C9 with no system and no options. And the next time they run, it has a lot of system and a lot of options. Well, sometimes it runs really fast and sometimes it runs really slow in that same configuration. So now we might need different cells, one for this configuration, one for that configuration. And the more configurations you add, the more complex that becomes. And so we end up with these mixed cells that would run, models we haven't really thought about yet, or configurations we haven't thought about yet, and it became a real problem. And so we talked about maybe we need more and more cells. We need to maybe add another warehouse, go back to the finished goods warehouse, add more cells because we need more options to produce our product. And I was like, well, hold on, before we add new cells, I want to see what a world-class company would do, because this looks okay, but this isn't perfect, right? There's a better way to do this. And so I told my boss that. I was like, this is okay. This works okay. And it's a lot better than what we were doing, but we're moving around people all the time. One section of the floor might be busy and the other section of the floor might not have anything because there's no configurations for that option set. So that all those cells would just sit idle. And maybe tomorrow we have orders for those. So then all those people would go from one cell to another cell. And we just bounce people around all over the system as we're building configurations as we were building. And so our predictability was still very limited. We didn't know when people were going to start and when they were going to end. All we knew is that your game was going to be done today. We didn't know when it was going to be done, and we couldn't and we couldn't guarantee like guaranteeing performance got to be difficult. Like hour by hour charts were very difficult to manage. Lines were running fast and then they're running slow, and then the people would leave and go to a different cell. It was chaos on managing how fast and slow the system would work. And it was just managing all these models became a nightmare, especially for me. So when you talk about adding more cells, that's more headache. And so I told my boss that. I was like, there's a real problem here. We got a problem with this, and we just can't handle the variation. The more variation we have, the more problems we have, and the more models we get, we're just going to have more and more problems. This is never going to end. He's like, I don't understand. What do you mean by variation? How much variation are you possibly talking about? Well, we have 50 main cabinets now. This is 50 main cabinets, right? This is like Toyota having a Corolla and a Camry and a Tundra and a Sienna. This is like a bunch of different models that we have, right? Different chassis that we can put stuff into. And inside those chassis, we have different BVs and different printers and different candles. If you add all that up, you get 18 million variants just for those 7 options. Well, we have 45 possible options for a slot machine. So we did the math on that. We're looking at 50 billion work instruction variants. Now, we had a system to present the work instructions, so it wasn't like we didn't know how to do it. We just couldn't manage all of the easy ones and all of the hard ones. The ones that were easy were going really quick, and the ones that were hard were taking a really long time. And so we needed to look at a company that knew how to do this. And so we knew that we were an integrator. We took a bunch of stuff from a bunch of suppliers and we shoved them into a metal box. And we thought about what Toyota did. We're learning the Toyota production system, but we never actually visited Toyota's production factory. We've only been doing this a couple of years now, and we're finally making money. So we're like, okay, we finally have the money to go out and let's visit Toyota and see how they're doing. And it changed. And Toyota was exactly the same as us. They're building a car and we're building a slot machine, but they're taking a bunch of stuff from a bunch of suppliers and shoving it into a car. We got monitors and we got PCBAs and cables and harnesses and brackets, and so do they. They're building a car, we're building a slot machine, but we have the same challenges that they do. So when I'm looking at their production line in 2008, I'm looking for possible solutions. How are they solving this problem? And it changed my entire view on variation. They had moving production lines running at a controlled rate all day, which is running a nice smooth rate all day. It was amazing how well it worked. And they had this pitching where the cars were at an equal space along the line. So you knew exactly when cars were going to come on and when exactly cars were going to come off. And the operators all had these work zones. They had this green line that would tell them, here's where you start, and this red line that told them, here's where you finish. And if you get to your red line, hit your and-on cord and you'll get help. And we noticed the problem solving on this was excellent. So the operator had this work zone that was kind of long, because sometimes they might have a hard option that might take them longer in the work zone, and they'll get caught up with the easier option and they'll come back in the work zone. And so as I started looking at the line and looking in more detail, I noticed they had a lot of options. 10 different models and over 1 million variants running down the production line, and the variants were running in a weird sequence. It was like, it wasn't by customer, it wasn't by model, it wasn't by geography. It was just weird. I didn't understand it at the time. I was like, there's got to be something to this. They're running a nice smooth rate all day. They're building a bunch of different models on the car. They're building minivans and sports cars and luxury cars on the same line in Japan. It ran nice and smooth all day. That's not something we would have done. We would have broken that into different lines. But they didn't do that. They ran it down the same line and it ran nice and smooth all day. There's something to that. And they were able to kit the material for the production line for the operator. So the operator had this nice little kit of material. They bring it in and they could build the car with these little kits. And they FIFO sequence material sometimes, where they bring the material in a first in, first out basis. The way they handled the material was just substantially better than what we were doing. And I knew looking at it, that's how I wanted to be, right? We have to get there. We've got to learn how to run this variety of product as smoothly as they do. So the first thing I wanted to do was build their moving line. Clearly there's something to this, right? They're building engines on moving lines, cars on moving lines. Clearly the moving line benefits them. So over here, I built a moving line. It's the first line that I produced, and this was our C9 line. And so here I ran all the C9 production down this line. We had 4 people in assembly, 1 in test, 1 in quality. It was about 40 feet long. We kitted the parts very similar to what we saw in Toyota. We learned a lot from the Toyota production system and how Toyota produces a car. And we wanted to produce a slot machine the same way they produced a car, because we had very similar issues than what they had. And we were able to do 60 units a day off this. We were able to double productivity on this moving line. And our flexibility was a lot better. It flowed consistently all day. It was nice and smooth all day. It was a moving line. It ran at a nice smooth pace all day. And when the line stopped, it created a real onus for problem solving. It helped us all the way around. The only problem we had was we still were limited by variation. We haven't quite figured that part out. If I had a C9 order that had all the options, the systems, the progressives, all the stuff in it, that ran pretty slow. And then if I had another order behind it that didn't have any options, it went to a customer that maybe had, ticket in, ticket out. They didn't have all the options that another customer would have. Those ran a lot faster. And so the line was still kind of herky-jerky. We'd have to turn the speed up, we'd have to turn the speed down. And I'm like, I don't see Toyota doing that. They run those very consistently. They can run all their models very consistently. So I want to learn more about how Toyota is doing that. So I went back And I went back to Toyota and I watched their line. I'm on the line, I'm watching it, and I'm watching it for many hours. And I finally realized that they're mixing in the hard ones and the easy ones. They're mixing based on complexity. That they're taking some of the hard ones and they're going to mix that with the easy ones, and that allows the line to run nice and smooth all day. So I want to do the same thing. I don't want to run a whole order at a time. I want to mix up these units so I have hard ones and easy ones running, so I can get maybe the hard ones taking me a little longer, and I get caught up with the easy ones taking a little shorter. And on average, I know how long it's going to take me to run. And so as I worked through on their production line, as I was on their production line, I worked through an algorithm in my head. I got back to the hotel and I worked in Excel and Yahtzee. It worked perfect. You know, I was like, this is going to be amazing. They call it a Hijunka sequence plan, and it makes a lot of sense. They sequence their product in a specific way so they achieve Hijunka. Hijunka is level loading. And if the line runs at the same time, same pace all day, every day, it's you can then level load how the material's brought in, how the material's brought out, how the software is brought in, how the software is brought out. You can level load all that stuff, and it helps solve a lot of problems. And it made a lot of sense to me. Mostly everyone calls this mixed model production, and Toyota calls it a Hijunka sequence plan. And I couldn't wait. I'm like, this is perfect. I want to run a moving production line where we mix everything down one line. And I don't have enough demand to warrant more than one line. One line's fine for me. I knew one line would be enough. So let's just do one line and we're going to mix them all up. And people thought I was crazy. You want to rip out all these production cells and put down one line? Why would you do that? Like, and it doesn't even make sense. Like, trust me, this is the real TPS, right? We can learn all about the terminology and the verbiage, all about the 7 wastes and all about value and flow, but the challenges we have in production are very similar to the challenges they have in production. So I want to run our production system the same way they run their production system, and they mix their stuff on their line, and it runs very smooth all day, every day. It's going to be amazing. And what I realized there was that, you know, running a bunch of stuff down one line isn't mixed model production. We weren't running mixed model production. We were just running chaos, right? It looked orderly, but it was still chaos, right? It wasn't as smooth as Toyota made it look. And so that's what I wanted. I wanted a nice, smooth production system, right? So I had this algorithm, I worked it out, and I went back to Toyota, and I was like, hey, look, you know, what do you think of this? Or how does that work? Or, you know, I had a bunch of questions for them, and they wouldn't answer the question. I read books by Dr. Leiker. I read books all over by Womack. I read everything I could learn, and everywhere I came across, it was that this is a proprietary secret for Toyota, right? This is not something they share. It's not something that they talk about. In fact, most plant managers that I talked to had no idea. You know, they knew it was all mixed up in their work, but they had no idea how all of that happened on the back end. That's what I wanted to know, because we had to do that on our side. We had to create a way to mix this production on our side. And so most suppliers are taught production cells because they don't have a lot of variation, right? When I'm an integrator, I'm taking all these different suppliers and all these different parts and I'm putting them into a cabinet. So my variation gets exponentially more complicated. But the build validator person only has 3 BVs. You know, they don't have a lot of variation on their side. But we're doing BVs and printers and systems and coin handling and progressives and all these different options and variations. Our variation explodes. And so I wondered why does Toyota, you know, teach one thing to their suppliers and do something else internally? Why aren't they like talking about what they're doing internally? Like, what's the big deal there? And what I realized is that's their special sauce. This is what makes Toyota Toyota. You can learn all about their supplier system, and you can be taught that by a bunch of different consultants, and you can read all about it in a bunch of different books. But when you want to run the Toyota production system, the way Toyota runs their production system, that's kind of proprietary. That's a special sauce for them, and that recipe is not known to everybody. And so they really control that quite well. It's what makes them efficient. It's what makes them predictable. It's what makes them flexible. And so I wanted to learn the algorithm. I wanted to learn how this thing works. And so what I'm going to teach today is the first algorithm I ever worked on. And one of the tricks of the algorithm was I wanted to make it easier. I wanted to make it the way, I wanted to make it trainable, and I wanted to make it easy for line leads and managers to absorb the information. See, one of the things Toyota's done well is they've taken industrial engineering and they've made it available to the masses, right? Teiichi Ohno took industrial engineering and he turned it into in a teachable moments that where he can teach all of his assemblers and his line leads and his supervisors all about waste and value and flow and all that stuff. And they took a very complex topic of industrial engineering and made it teachable and learnable to the masses. I want to do the same thing for this. As I went online, I looked in like how does mixed model production work and all the all the algorithms. I came across all this documentation that just looked confusing. And I'm like, there's no way it's this hard. It has to be simpler than this. So I went back and I'm like, what are we trying to do exactly? If I have all these cars up here at the top, I want to break those up into days because I want to be able to get things done in a certain day. So that's part of my scheduling. And then I want to run this down a production line. This is kind of what we did. We ran this down this line here where I'd have a model in day one where I'd have a whole model running. And then I'd have a more difficult model here and then a sports car model down here. And the line would run, okay, and then really slow, and then super fast, and the line would be up and down all day, or the operators would stand around a lot. And I didn't want to do that, right? We were already having that problem. Like I wanted to get past that. So I wanted to get to this mixed sequence where I'd have an easy one, and then a hard one, and then an easy one, and then a hard one. And I'd mix up the orders intentionally so the line ran nice and smooth all day. And that's what we're going to calculate is how to do this mixed sequence by day. So I can run one line, run all my variation, and runs nice and smooth all day long. Now, before we get into this, there is some stuff you got to know ahead of time. One, you need some variation, right? So if all you do is one model, that's not mixed model. That's just model production, right? I need my demand to fluctuate. If I have 5 different models, let's say, but they do the same amount every single day, that's still not mixed model production, right? I want, if I'm running, sports cars and SUVs, some days I have a lot of sports cars, some days I have a lot of SUVs. I want to be able to mix those up so that so the line runs nice and smooth all day and the demand can fluctuate for those. That's the challenge I was facing. We also had a lot of manual labor content for this. Assembly type work is easy to balance, right? It's easy to move work around and balance it. And so that's what we're working on here is how to balance the work content. If you're doing machine-based work centers or you have machine-based centers in your factory, you're probably using Kanban between those. And if that's your deal and you have a lot of variation in your machine-based work centers, you want to be able to iron that out. It's a different algorithm. So that's a different training session. But for here, we're working on assembly type of work. The other thing we want to do is we got to be able to pick one unit at a time. If I'm running back in this production, I'm looking at this bottom line here. I have model 1 here, and I have another model here. It's completely different than this model. It's a totally different bill of materials. And this SUV is completely different than that. It's a completely different bill of materials. If I presented all that material to the assembler, it would just be a mess. I got to be able to pick this material and deliver it in sequence to the line at the right time. And so that's this kitting one unit at a time type of stuff. The other thing I need to do is because I'm going to be mixing up my orders, and I'm going to be taking hard ones and easy ones and putting them together. And so the orders are going to get broken up a little bit. We got to be able to consolidate those. I got to be able to run them down production, have them come off production, so I can then consolidate those into a marshalling yard. So here's what Toyota does, right? So they have this manufacturing center down here, and the manufacturing center will then, as the units get done, they go into this marshalling yard, or they'll get slotted in the marshalling yard by whatever customer they're supposed to go to. And when that slot is full, it goes onto a car transporter, onto a rail, and off it ships. So the line runs super smooth because they're able to mix those up a little bit, and they'll deal with the consolidation in the marshalling yard. So we want to do the same thing. We want to be able to marshal these units as they're coming off our production line. We're going to run our line super efficient, and then we'll deal with the marshaling of it later. And it turns out to be very simple, right? It's very easy mathematically to figure out where to slot these things, and then when to tell the system, hey, this one's going to be done at a certain time, and this one can ship out. And we can organize our trucks and all that stuff. It ends up being pretty easy, to be honest with you. And so that sounds great, right? We have this moving production line. We've got one to mix models up and all that kind of stuff. Great. We can talk about it all day, but we want to run it. And so we want to see how this actually works in real life. So we have a simulation that we do. And the simulation we do is we pretend that we're Lego Matrix, and we're making Lego bots. And those come in 4 models, A, B, C, and D. Model A, Model B, Model C, Model D. And we want to design a production system to meet that demand. And so we're going to be doing assembly. And we want to design a production system for the assembly type of work. We're going to order material from the supplier, we're going to assemble it, and then we're going to ship it to the customer, get paid, and use that money to buy more material, assemble more product, and deliver it to the customer. And that process will just continue over and over again. So the workshop that we create is a hands-on work environment where you get to build a line from the ground up. And we made the math super easy on this so that anybody can learn how to do this. Line leads, assemblers, engineers, finance people, CEOs, doesn't matter. You can use this to learn how to run a Heijunka sequence plan and have it run nice and smooth on your production line. And if we're going to run this, the first thing we need is some demand. I need to know what I'm going to run, right? And so this is where we start off, is the demand. I have 45 minutes in the workshop to set this up and how we're going to run this. And we're going to run 5 minutes for production. So production time is 5 minutes to run this. As I buy a Lego from the suppliers, they're $1 each. Material's not free, and I don't have unlimited money. So I don't in this simulation either. I got to be strategic on how I buy the material and how I get it from the supplier. And that creates a big problem for the teams as they're getting this thing started. Obviously, I want to minimize my labor, and I want to make sure that I run this as cost effectively as possible, but I want to get all of this demand done. Now, most people will look at this and they try to make orders at a time. They'd be like, this order 2 is $440. I need this money. Go produce these. Well, that turns into a real mistake to happen, right? It's a real bad problem. And they would run a production line trying to run order 2 down. I run out of money buying the material. I have a lot of stuff running around the floor. I got parts all over the place. You end up with the same stuff that we had. It was an expensive process that wasn't very productive. And the other thing we wanted to do when we're putting this together is, the question that always comes up, I should say, is what are we building exactly? So model A, B, C, and D, what are we putting together? How are we putting this together? How do I design this production line, knowing what I'm putting together? And so here's what an A looks like, and here's what a D looks like. And so A is super simple. It's only 10 parts. Remember, a Lego is only $1 each. This is a $10 assembly here. Model Ds are far more complex, and our instructions are very clear on how to put this together. But this is the D is way more complex than the A is, right? And so, okay, the people know this now. They see the Ds and they see the A's, and they know the orders we're building and the quantities we're supposed to build. How do we solve this? So you have a couple options here. You can do like what we did in the first version. You have a model A with a bunch of, or a version A with a bunch of lines on it, and that's how we produce. Or you could have version B with a bunch of cells in it, and each cell will run its own little variants on it, and you could produce that way. But you have the same problems that we had. It would be expensive, it'd be chaotic, it'd be hard to manage. So I wanted to do something different. I wanted to do it down one line. And we wanted to run that line on a controlled rate. I want to do the A's, B's, C's, and D's all down one line. And I wanted to run it at a nice controlled rate. And people ask them, what's the rate? Is the rate takt time? Yeah, the rate's takt time. It's based off takt time. The takt time is the rate of demand, right? And so I want to run the line so I can meet my demand. So takt time is my guideline for that. And you'll work through that on the calculations. We want to balance the work content for each operator. So each operator has the same work content for a given model. We want to mix up the units so that the hard ones and the easy ones get mixed together. So maybe on the hard ones, I might, fall behind in my zone a little bit, in my work zone, my area space that I work in. And on the easy ones, I get caught back up again. And I want to be able to mark off where it's okay to work and where it's not okay to work. So I'm position 3, for example, I have a green line that says this is where position 3 starts, and I can start working there. And I have a red line saying if you get to this point, hit your end on light, because there's a problem there. And I have a zone where it's clear where I should work and where I shouldn't work. And we always get this question of, is it really better to run this down one line? Like, why would you run this down one line? Why not just have a bunch of different lines with a bunch of different models, right? Some of these models take twice as long as other models. Why mix this up? Like, it just seems more complicated than it needs to be. And sure enough, we want to do this because we want to get the same advantage that Toyota has. Hard ones and easy ones run together, and the line runs nice and smooth all day. Same pace all day, all the time. I'm not running lines that run super fast because they have easy models, and other lines run super slow because they have hard models. Or maybe the line itself has a hard configuration, so it runs really slow, and then an easy configuration runs really easy. I want the line to run at the same pace all day, every day. And I want to sequence the flow into the line so that I know it's going to run at the right rate. I'm going to be able to meet demand, and everything's going to come off just fine. And so the sequence I'm going to run for this is DDD, C, BBA. That's our sequence, DDD, C, BBA. Mixing up some hard ones with some easy ones. The D's are hard and the A's are easy. And so I'm going to mix up the hard ones and easy ones so I can run nice and smooth all day. And the question is, how do I know that? How do I figure that out? Well, we have a mixed model calculations worksheet on McFallstech.com. That's our worksheet that you can, that's free download. You can go ahead and download that, and that guides you through the calculation step by step. We're going to do it together here. And we're going to learn this simple algorithm that we use as part of this worksheet to go through this whole sequence here. And it's really easy math. So don't be scared by this. It's not hard. It's not difficult. It's just a different kind of algorithm you come out with. And in the result, you're going to have a line that is nice and smooth all day. So let's get back to our challenge here. And this is all the stuff we're going to run. And so I'm not going to worry about the orders because that'll get handled in the marshalling yard, right? I want to run the models nice as efficiently as possible. As the models come off, the marshalling yard will figure out which orders can ship first. And as soon as it can ship, out it goes. And so the one thing I want to know here is how many A's do I need to build and how many B's and C's and D's do I need to build? So if I look at the A's, I have 1 plus 1 plus 2. That's 4 A's. So I have 4 A's, 8 B's, 4 C's, and 12 D's. So 12, 4, 8, and 4. So that's how many models I'm gonna build for each model configuration, right? I want to figure out, like, what's the number that divides evenly into all those? So if I have 4, 8, 4, and 12, what divides evenly into all those? Well, 4 does. 4 divides evenly into all 4 of those numbers. 2 does, but 4 is bigger than 2. 6 doesn't divide evenly. 4 is the number that's the biggest number. That's our greatest common denominator. So the next thing I want to know here, so I know the model, I know the how many quantities I'm going to build in my GCD. Now I want to know the cycle time. So we're going to go through A's, B's, D's, and C's and do some time observations. How long does it take to build an A, and how long does it take to build a D? Well, the A's are 25 seconds long, and the D's are 60 seconds long. That's from time observations now, right? Same tools we used in Kaizen event. So 60 seconds to build a D from start to finish, and 25 seconds to build an A from start to finish. Great, I have good information there. Now that I have that information, I can begin to put my sequence together. I know I need 12 D's, and I know my GCD is 4. So I'm going to divide the 12 by the 4, and I get 3. And I do that for all my numbers here. So 4 divided by 4 is 1. 8 divided by 4 is 2. So I get 3, 1, 2, 1. And now I want to put these together from the longest model to the shortest model. I want to mix up my hard ones and my easy ones. So I'm going to start with the hard ones and go to the easy ones. And that's going to be my sequence. So I have 3 D's. I have 1 C. So I have D, 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 C, B, B, A. That same sequence we talked about earlier. That's how that gets calculated. That's the sequence I'm going to run that allows me to mix up my hard ones and my easy ones so my line runs nice and smooth all day. Great. That's and think about that. We did that without hardly any math at all. That was great, right? And so now I just need to know how fast does the line need to run and how many people do I need? That's my next step here. And so I know my sequence. How fast does the line run? We'll use takt time to help us guide us through this, right? So takt time is our time available here is a 5-minute production run, 300 seconds. I have 28 units total. If you add up the A's, B's, and C's, and D's, you get 28. That's 10.7 seconds. So I need to produce a unit every 10.7 seconds to meet demand. Perfect. Next thing you need to know is how often, not how often, but how long does it take an operator to build a model on average? On average, how long does it take to build a model? So knowing that some are going to be easy and some are going to be hard, and I have more of some and less than the others. And we call that an average weighted cycle time. So I have my cycle time. I want to weight those by how often they run, and I want to be able to average that out over the whole demand, right? So if I have 4 A's and I have 28 total, 4 divided by 28 is 14.3%. 14.3% times the 25 seconds to build that model is 3.6 seconds. 3.6 seconds is how long it takes to build an A on average for this, considering how often I run them and how easy they are. I add all those up and I get 45 seconds. So the operator on average takes 45 seconds to build the models for this mix. Now keep in mind that that's because of how they're weighted. In other words, how many, with the quantity of each model that I have. I hope that makes sense. If I had 12 A's and 4 D's, I still have 28 units. So my takt time is still 10.7, but my average weighted cycle time now is weighted more by the A's. So that brings my average weighted cycle time down a little bit. So instead of 45 seconds, I'd only be 35 seconds, right? So we use this to figure out how long on average will an operator build a unit. Well, how long will it take on average to build a whole unit on the production line, considering how difficult they are and how often they run. So this is the math we use for that. Now I can use this 45 seconds to figure out how many operators I need. 45 seconds is my average weighted cycle time. 10.7 seconds is my takt time. Divide those two, I get 4.11. I can't have 0.11 of an operator, so I'm going to round it up to 5. I need 5 people on my line. I know my sequence, DDD, CBBA, and I know how many people I need, 5. I can now take that average weighted cycle time and divide it by my number of operators and get how often will a unit come off the end of the line. A unit comes off the end of the line on average every 9 seconds. So every 9 seconds, a unit comes popping off the end of the line, because I'm taking my average weighted cycle time and I'm dividing it by how many people I have, so that each person gets the same amount of work, right? I balance the work content between all the people on the line. Now keep in mind, the 9 seconds is not how much work each operator gets. That's just how fast the line moves. The line produces one every 9 seconds, but the operators may get a little more work for a harder model and a little less work for an easier model. So we got to figure that part out now. I know I need 5 people, so just divide the cycle time by the number of people. I got 25 seconds for an A, divided by 5 people, that's 5 seconds per person. Each person, when I'm building an A, gets 5 seconds of work content. When I'm building a D, those take a minute to put together, and I have 5 people on the line, so that's 12 seconds per person. 12 seconds times 5 people is a minute. That unit will be done. So each person gets 12 seconds worth of work to do. My pitch is 9 seconds, right? That's what we said. Every 9 seconds, a unit comes off the end of the line. So every 9 seconds, this one comes off, and then 9 seconds later, this unit comes off. So I'm producing a unit every 9 seconds. Well, when I'm building a D, I have more than 9 seconds. So it's going to carry me, if this is my pitch here, my distance between my units, my work zone needs to be bigger than that, because sometimes my work content is a little longer than that. Everyone comes off every 9 seconds. Well, I have a little more than 9 seconds worth of work to do. I need a little more space to give me enough room so I can work on the hard ones, but I'll get caught up again with the easy ones. So this is my green line where I start, and this is my red line where I end. The operator will work towards the red line as they're building the harder ones, and towards the green line as they're getting towards the easy ones, and they'll bounce back and forth inside their zone. They'll run nice and smooth all day. Perfect. Wow, we're getting close. I know how to balance the work content now. Now I just need to design the line. So I have all the stuff here, but I don't have our dimensions. I don't know how big to make the line now. So I want to, if this is my pitch, this is a unit I'm building, here's an operator, and a unit I'm building, here's an operator, this is the distance between the units. It says 9 seconds, one's produced every 9 seconds. Well, what is that physically? Well, what I need to know is if I'm going to build these units, how much space does each operator need? These are the Legos I'm building. So if I have an operator in operator 1, an operator in position 2, and an operator in position 3, how much space does each operator need to build? Well, if I'm building a unit, 1 foot isn't enough space. If I have 2 people building next to each other, we're going to be banging into each other. 3 feet is too much space there. I don't need that much space, but so 2 feet seems to work really well. So that's perfect. That tells me how to design the line now, right? So think about this, right? So a unit is pitched every 2 feet, and a unit comes off the end of the line every 9 seconds. So I go 2 feet every 9 seconds. So let's figure that out in speed. So 2 feet, 24 inches, every 9 seconds is 2.7 inches per second. That's my motor speed. So I need that so that I can control my motor. This is how fast the motor needs to run. I have almost everything now. I have the number of operators, I have how fast the motor needs to work, I have my sequence plan, I have all this stuff. The only thing I need now is the total size of the line. And this is the most complicated part of this calculation. It's not complex math, it's just hard to work through mentally. And so I need the zone size. And so if I'm building a D and I have 12 seconds worth of work to do, let's say I'm building my DDD, CBBA, my sequence here, I'm building my first D, I'm gonna be at my green line. I'm starting out, I'm starting my build, right? And it takes me 12 seconds to build. I move 2.7 inches per second, so I move 32 inches physically down the line. Now remember, the units are pitched 24 inches apart. So when I'm done with this and want to go pick up my next unit, I'm going to go back 24 inches to the 8-inch line. Now I'm out in my work zone a little bit, and I got to go out another couple inches. I got to go out another 32, like 32 and a half, whatever it is, and it ends up at 41. Go back 24 and build another D. It takes me way out to 50. Go back 24 and build a C, and these are a little easier. So now I'm gonna be creeping back in my work zone, because now I'm mixing up the easy ones with the hard ones, and when I get back to the D, I'm back at 0. So DDD CBBA will cause the operator to start at the green line, go all the way out in their zone, and come back in their zone. All the way out in their zone, come back in their zone. Each operator needs 50 inches of space to accommodate their sequence, to accommodate how difficult their sequence is gonna be. And that's all I need. I have everything I need now. Think about it. DDD CBBA, 5 people, a unit every 9 seconds, 2 feet apart per unit. Each person needs 50 inches worth of space. I need 5 people on the line. I know how big the line needs to be. I know exactly how to load them on the line, the exact sequence I'm going to run. I know everything I need to know. And so we got to see this visually though, because that sounds like, that sounds great, right? Oh, that's awesome, but what does that mean? Like, I'm not sure that makes any sense still. So let's look at this visually. So we're going to show a line that has a moving line. Then we'll show another line that has the same moving line but adds a model to it, so you see the model, the problem that creates. And then we'll see what happens when we actually use the equations and run the system according to the Hijunka sequence plan. So here's how it actually looks physically, by the way. This is a line that we put together. And this company has done a great job putting this together, by the way. We've helped them out, but they've really done wonders with being able to put together some neat stuff here. But they're building cabinets here. And so I have an operator sitting here. I've got a yellow line here. That's the warning track. The red line's the end of the zone, and the green line's the beginning of the new zone. And so as it's moving down the line, it's very clear where operators are supposed to work. We have our work instructions that we can present. We have a kitted part of materials. It's moving down the line. I can move up and down. We've done a lot of good work here engineering this. This is something that we help provide. We design the engineering, we do the software, all that stuff. And so putting these lines together is kind of our business here. And so how would this run? Well, this is how this is going to run. I'm building the Model A, building them all day long down the line. Perfect. Works great. I have green markers show me where I can work. I have red markers show me where the line should stop, all that kind of jazz, right? This is awesome. So what happens though if, and this is great as long as I'm running the same model, but what happens if I'm running a different model? If I'm running this, and this all runs great as I'm running an A, but then pretty soon I start running into problems here because not everything is in A. All of a sudden a B pops in, and let's take a little bit longer. And so now we all gotta wait. I don't want to pick up the game, the unit early, so I have to wait for it to hit my zone until it's in the green zone. So it doesn't help me to pick the unit up early, right? It doesn't help me to do that. So I want to make sure I have my work zone where it's okay to work and where it's okay not to work. And so I need a different way to do this. I got to be able to mix this up somehow. I gotta mix up the easy ones and hard ones. And so when we use the calculations, this is what it looks like. So let's take this A here. We'll take this front part of the A right here. And as it crosses the yellow line, we'll call this out. And so we can see how long this thing actually runs. So go 1, 2, 3, 4, 5, 6, 7, 8, 9. Every 9 seconds a unit's coming off. Every 9 seconds a unit's coming on. I can mix up my easy ones and hard ones. My work zone sign is big enough, so I always have something to work on. Everyone stays productive. Perfect. We did everything we need to do to be able to run this line nice and smooth all day. Our calculations were great. That's all we needed to do. Now we can just go design. So as part of our workshop, we'll actually put this together. The people will put together a production line and actually run it down their own line. This is two different teams here, 2 different sessions, and they both produce lines, and they both look very similar, right? So they'll pitch them at 2 feet apart. The people can work together nice and smoothly. They have zones here where it's clear where the end of the zone is. Perfect, right? If you compare it to Toyota, it's actually very similar. Toyota builds cars, but it looks very similar. I've got these markers here of what the model is going to be, and I have lines as to where it's okay to work and not work. And so this is great. We're running just like Toyota. This is awesome, right? A very simple algorithm, very easy to use, allows me to run nice and efficient. If you look at the metrics in terms of how this runs, batch production was 30,000 square feet. When we got the mixed model production, down to 3,000 square feet because we're only running one line. Resources 243 down to 40. So a lot less people, a lot more efficient, a way better way to run production, and it runs nice and smooth all day, every day. This is great stuff. And so our inventory went down, our productivity went up, our first pass yield went up because we're running nice and smooth. It is a game changer. If you're running high mix assembly type of work, this mixed model production, this Hijunka sequence plan can really change how you run your production floor. And so that's kind of the end of the webinar and the end of the presentation. And so if this is interesting to you, go ahead and reach out to me either on LinkedIn or through or call me on the phone at 702-683-6376 or at mail@mcfallstech.com, and I'll be glad to answer your questions. And we can always work with you together if you really find this interesting. Right now, I'll turn it back over to Darlene. I'm interested to know what questions you might have, what questions you submitted as part of this webinar.
Thank you, Greg. We did get a couple of questions. So here's one. What if we do fabrication work that uses a lot of machinery? Does that still work?
So this works as part of assembly type of work because it's easy to balance. When you're using machinery type of work, it's a little more complicated. having to deal with the machine cycle times. And so we have a slightly different algorithm for that. That's a different presentation, a different workshop for that. So this is assembly only. If you're doing fabrication and you're interested in that, reach out to me either through LinkedIn or through email, and we'll be glad to work with you on that.
Okay, here's another question. Is this limited to only one assembly line, or is it possible to have more than one assembly line?
It's a good question. You know, Toyota has multiple assembly lines in Georgetown. You can certainly run more than one line, even in the same factory using the system, and you just need to know what demand is going to run on what line. And this algorithm will mix up that demand so the line runs nice and smooth all day, every day. You know, Toyota has a problem where, you know, the lines may run too fast. So they can't run everything down one line because the takt time would be so small that the operators would spend more time moving back and forth actually building a unit. And so you know, for us, we didn't have that problem. So, you know, we weren't at the same volume that Toyota was at, so we could run everything down one line. But if your volume is so high, you need to break it up between multiple lines, you can do that. You can break it up between multiple lines and run multiple lines in the same factory. And we have customers that are doing that now. They run multiple lines in the same factory, and each line uses the Heijunka sequence plan, so it runs nice and smooth all day.
Okay, we've got another one here. How much variation in work content can this algorithm handle?
It's a great question. So we have a customer right now that runs they run a bunch of different models, and one of their models takes about 6.5 hours to put together, and another model takes only about an hour to put together, and we're able to mix that down the same line. Now, obviously, when you're doing a 6.5 hour model, each operator is going to have a lot of work content for that. When you're building an hour, the operator is going to have much less work content for that, and so that may increase the zone size a little bit, but you can mix a wide variety of work content down the same line. If you find your zone size is getting a little too big, you can break those up so you can have your really, really complex ones on one side and your really, really easy ones on the other. But you'd want to keep that on one line if you can. We found that we have a lot of advantages of running this down one line if we can.
Okay, we've got some more questions coming in here. So how about this one? What is the normal lead time to kitting models, and must they move with the line?
So no, they don't have to move with the line. You can FIFO sequence material next to the line. You see that if you go to Toyota's production line, you'll see that these FIFO sequencing racks all over their production floor. But they do kit their production stuff, their production material on the line for the operators, especially if the operator has to work inside the car a lot. They'll kit them in little bins, so the operator doesn't have to leave the car to get material and come back. And so they use kitting where they can to take waste out of the operation. And the kitting process depends on how many materials you have. So if you have a lot of small materials, it's really easy to kit. If you have a lot of big materials, it may take a little bit more to kit. And same deal that you run in production, right? You want to know how long it takes to kit the stuff, so you know how many people to have in the kitting, on the kitting side of it. What you don't want to do is kit way far in advance. You don't want to do the kitting a week ahead of time. You want to try to do it just in time. I want to produce the kits at the same rate the line's going to run, and I want to do them as close as possible to the line as I can get them, because I want to be able to give the system a chance to be responsive. If something else has to become more important, if something else has to push out because there's some issue, I can go ahead and I can change that. And because everyone's working just in time, everyone else is none the wiser. It makes my system way more responsive at dealing with changes. So if you're gonna do the kitting, all I would say is make sure you're doing the kitting in just-in-time configuration, and that when you kit the materials, you find a way to present them so when they get to the operator, it's nice and smooth and easy for the operator. It's not just a pile of stuff given to the operator.
Okay, Greg, we've got another question. What if we don't build to forecast, but we build to order in a high mix with different demands daily?
We do too. That's what the slot machine business is. We don't have, we're not building to inventory either. We don't have, Toyota has kind of a nice advantage where they can build to the dealerships, right? They can build to a sort of inventory with their dealerships. We didn't have dealerships, it's slot machines, right? So we're building to order as well. And so for us, we would do our Heijunka sequence plan. We would plan that out the day before. And that gave our sales team a chance to move things in and push things out and all that kind of stuff. And we could understand in the system what we had materials for, what we didn't, all that kind of jazz. So when it ran the production line, when it actually made it to production, it ran nice and smooth on the production But we were the same deal. We built to the order. We didn't build the inventory. So it works okay in a build to order type of model.
Okay, I've got another question. How would you choose a zone size if the sizes of different models change?
So it depends on the pitch, right? So your zone size depends more on the pitch of the unit. And that's because when I get to the end of my model, I have to go back and get my next model. And so the pitch between units really controls the zone size there. So if I have some units that are really small and some units that are really big, and I try running those down one line, I may have a pitch issue because I have to pitch to the biggest unit. If I have a really small unit, I may have a lot of walk time there to deal with that. Toyota has this problem as well, right? So they have Toyota Tundras that are very long, and they have Toyota Corollas that are very short. And so they don't run Tundras and Corollas on the same production line because they have a pitch issue between those two. So you might have the same problem there. We have a pitch issue if you have really small units and really big units. For most of our slot machines, they fit in basically the same base. So we can run everything down one line for us on the slot machine side. But if you have an issue with the geometry of the part, you may have to run two different lines there so you can pitch them in two different ways. And that allows you to calculate the zone size nice and effectively.
Okay, I think we've got time for one last question. How far ahead is the planning done?
Great question. So, in Toyota, they'll do like a forecast type of deal of what they think they're going to sell. And there's different ways to look at this. It's about a month out. They do this planning about a year out, but they really about a month out is where they really solidify what's going to happen because they don't know what's going to happen with gas prices or unemployment rates or who's going to buy what, and these cars are popular, these ones aren't popular. So they'll do it about a month out. Now the month out tells me how much I'm going to build here, but I only do the planning in Toyota about 3 days ahead of time. I do my high junket sequence plan 3 days ahead of time. At Bally, we couldn't even get that far. We could only high junket sequence plan a day ahead of time because a lot of stuff happens with pushing things out and pulling things in and all that kind of jazz. So we can only do it a day ahead of time. So when we're talking about the lead time of doing a high junket sequence plan, we want to make sure we give enough lead time so people can execute, but we don't do it so far ahead of time that we make it inflexible. So for us, doing it the day before at about 2 p.m. the day before is where we create our sequence plan. That sequence plan then goes to the supplier, and that tells them how to deliver the cabinets and everything just in time. So we get the material just in time the next day coming into the production line in the exact sequence we needed it. So it's about a day ahead of time.
All right, thanks for all the questions, and thank you, Greg, for an insightful presentation. We will be sending a recorded link for the webinar replay to each of you next week. This brings our webinar to a close. Our next scheduled webinar will be on Thursday, June 14th, titled Lean-Driven Project Management with Norbert Moore-Harris as your presenter. Please visit ame.org under the AME Events and Training tab to click on the AME Webinars for more information and to register. Please don't forget to fill out the short survey that will be in your inbox. Thank you, everyone, for attending, and have a great day.